So yes, so, and this is, I think, is a general situation. It's just that you need to get, as a mathematician, you must stop thinking about logic being special. It's not a holy cow. If you are able to mold your definition of space or whatever you study, if you're able to mold it to your desires, you should be able and brave enough to do the same thing with logic. It's not that different.
That's a very good slogan. And this is why I wanted to have you on the show, is your ability to sloganize these somewhat non-trivial ideas. Sorry, maybe if you don't mind, I'm going to transition here slightly. So here's the transition. Grothendieck is like, in my view, was a master at doing a similar kind of move, which is take the situation he wished was true, take the world in which he wished to live, and then build basically a category or build an environment in which those things are true, right? You have these bad, spaces of whatever, of algebraic varieties that you don't like. Build, an environment where these things don't arise, or you have bad topologies. Build a new topology in which, only, or like, that gives you more freedom to define things. And basically you mentioned these two, roughly these two big worlds of intuitionistic worlds, of models of intuitionistic set theory, or models of intuitionistic logic. You said one of them was the computable one, and we talked about that one to a certain extent. And the other one was the sort of the topological one. So why don't we try and give an idea of what a topological intuitionistic.
Okay, so let's do that one. But before that, let me just point out one other thing. Like, I'm really serious about logic should not be considered special. Okay, so you say Grothendieck was a master at manufacturing the thing he wanted to have, right? Which people thought it's not there, but then he made it be there.
Right.
It was not easy, right? It took a genius. It is quite complicated, but it was there. Okay. So I think it is always good to ask yourself, do I know of a similar, simpler situation that is not considered mysterious because, capital
some genius case.
Okay. So do we know of one? Yes, we do. Okay. People manufactured a certain thing so that they were able to solve equations better. That certain thing is called complex numbers. To my mind, there is very little difference between Grothendieck manufacturing the schemes and the toposes versus, conceptually, it's the same thing. Manufacture new mathematical objects of great importance, right? Square root of -1 is one such idea. And it took a long time for it to be accepted. Non-Euclidean geometry
that's a great example. Also, I was thinking the square root of 2 seems to also be such an example.
It's an even older example where they didn't have a good handle on it. I think the problem, I don't think there was any doubt that the diagonal of the Unix square has a length. The problem there is that this length is really unusual. It's not a ratio of two whole numbers. So there it was, I think, easier to think it's some kind of, it's there,
but
it's there,
we need to somehow
but
get
it's
our hands
weird.
on it.
Whereas with the complex numbers, they were not even there. They're called imaginary for a good reason. They're not even there, right? So that's another one. Another one is
right. You mentioned non-Euclidean geometry.
Non-Euclidean geometry is another one, right? You're sitting there. It's totally obvious that the fifth postulate holds, and you say, "How could it not hold? This is impossible for it to not hold." But somehow, you through conceptual analysis, you let your imagination free. Plus, you are good at doing the technical things. You manage to produce it. So these are, I think, these examples of discoveries, of these kinds of discoveries, they're similar to what Grothendieck is doing. So what maybe we can say about synthetic mathematics is that there is an additional move that we make. which is we are very careful about the language with which we're going to with how we're going to do it. Not only are we going to build a model, not only are we going to say, oh, the complex numbers are a pair of reals, oh, you know, a scheme is a sheaf on la 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 la. We're also, at the end of the day, we're going to say, okay, we produced something. What is a good way to speak about it directly? And as it turns out, in many cases, the answer is intuitionistic, higher order logic, because the thing you made is a topos.
Right. So there is
one example which is not like that, which is also super important, which is the answer is homotopy type theory.
Oh yeah.
Right.
I'm sorry.
Because that one needs because there you did something very, very new and important with equality. You radically changed how you understand equality. It has a lot of important consequences, but there the language seems to be type theory.
Okay. So let's see. The mantra is find the language in which it is natural to talk about the objects that you care about. Then find a logic in which, you know, for that language. Which
logic ought to be imposed on you once you know what the structures are, right?
Right. And then figure out what that logic of these things you're talking about is. And then, you know, all these pathological objects you don't want to have just are not there because you can't even talk about them.
Right. So we are willing to change logic in order to get the things which would otherwise be impossible to get. Infinitesimals, all functions are computable. I can throw this one in, right? The reals are countable.
Yes.
Right.
I had that one in mind, but
So every, you know, things like or in synthetic topology, every map is continuous.
Great. All right. So I feel like it would be fun now, but you can tell me if you'd rather do something else to try and describe
yes,
at a high level is kind of
let's do
topological.
That. Okay. Let's do that. Okay. So so the way I like to think about this is
I'm sorry, just before you start, I want to say this very quickly because this seems so obvious to me that I forget to mention. But a topological space, right? If you know what that is, you know, it has this notion of opens and closed. But that naturally supports propositional, you know, intuitionistic logic, right? Where you have ands and ors and implications. And that, for a general topological space, even a very reasonable ones, right, which are opens sets of, you know, the unit interval, is not classical, right? That the interpretation of intuitionistic logic over, you know, the open sets of the real numbers does not admit the excluded middle, right? So that's the first, just here is a very simple topological situation where you can think about logic and it's not classical logic.
So you actually very nicely explained the first thing that needs to be explained when you start thinking about topological sheaves and how they relate to logic. So first of all, you can ask, when is the topology of a space classical in terms of logic? So we could just say, first of all, unions are or, you know, the union is a union is or, the section is and, conjunction. There is okay. So well, so it's going to be classical if if the complement of an open set is always open.
Right.
So it's a nice exercise for the listeners to figure out whether there are any non-trivial topological spaces with the property that the complement of an open is always open.
Right. That's nice definitely not true for the reals, right? Like
for reals, this is obviously not the case, right? So okay. So in one way to think about how intuitionistic logic works is that you say we're going to change what the meaning of true is. If you think that the classical understanding of true is that something like it is the case, right? But in intuitionistic mathematics, we can measure how it is the case, or where it is the case, or when, right? in the realizability world, we would measure how much something is true by considering what algorithms compute that thing. So in the topological world, let's just take something simple like our planets, okay? Sheaves on a sphere, okay? So we're never going to ask, is a thing true? We're always going to say, where is it true? And there is going to be a catch, because we're doing things topologically. We always want this truth to be stable. What I mean by that is that if you wiggle things a little bit, it shouldn't change. And this is a notion that is familiar to topologists. That's kind of the point of an open set.
Yeah.
But if you have an open set and there's an element of the open set, if you have a point in the open set, if you wiggle it a little bit, it's still in the same set.
Right.
So that's the idea that I have in mind when I say it has to be stable like that. Okay, we don't want things to change, truth to change to be changed by arbitrarily small perturbations, because that's not going to be very. It turns out that's not very interesting. Okay, so now you take something like the temperature is. Let's take a statement. Temperature is below 0 or is equal, or it's either negative or it's greater than or equal to 0. Okay, current temperature is less than 0 or it is greater than or equal to 0. Okay, so now we don't ask, is this true? Instead, what we ask is, where is it true? And now you have to know a little bit of this technology of sheaves, but what's going to happen is the following. You will take the largest open set. Let's see, let's get this right. We're going to take all the places on Earth where the temperature is less than 0. Okay? And assuming temperature varies continuously, so that's another thing that's going to happen. Sure. This is going to be an open set. Okay? Now the other one, we need to take the largest open set where the temperature is greater than or equal to 0. So we want places on Earth where temperature is greater or equal to 0, but stably. If you move just a little bit away, it's still greater than or equal to 0, right? So for instance, if there is some part of the Earth, if it's a big part, where the temperature is exactly 0 there, then that part will be considered, that one part will be included in our area, because it's, you move around,
you wiggle around, it stays at 0.
But if you're on some line where if you move a little bit to the right or to the left, it suddenly drops below 0, that would be excluded.
Okay.
So now we ask, did we cover the whole Earth? And the answer is no. The places where this is going to happen will include places where it's less than 0 and these stable places where it's greater than 0, but we will exclude this frontier where we pass from negative to non-negative. Right. That will be excluded because that's where this is not stable. Right. Arbitrarily small perturbations push you one way or the other, which is to say that the statement is not true everywhere.
Right. All right.
However, it would be true everywhere, maybe, if we are so misfortunate that some years from now, the temperature everywhere will be greater than 7. If the temperature will be greater everywhere, greater than 7 everywhere, then of course it will be. But you can imagine how it can happen that it isn't.
Right. So we're talking about a statement.
Yeah. You get into the
about calculus.
Yeah. So what does this give you? Okay. So this gives you so what is going to happen is that you will end up thinking very much about what happens in a neighborhood around the point. And you will want to consider statements which are stable in a neighborhood around the point. And we haven't mentioned the other condition, which is the gluing condition for sheaves, which says, and by the way, if you want to figure out what happens on a large area, you're allowed to chop it up into some open cover and then study what happens on every possible. And this is precisely this local kind of reasoning that in analysis is quite common. So the sheaves on a topological space have the logic has a built-in idea of local reasoning.
Right,
And
right.
analysts are very familiar with the idea of reason locally, right?
Yeah,
And
yeah,
this
yeah, yeah.
and this is the formalization of it. So I find it. I would imagine that they would really want to learn about a formal system that allows them, that tells them that the thing that they know heuristically, which is local reasoning, can actually be made precise.
Okay, so let me again try to summarize what you're saying. You're saying here is a different topos or a different world. Let's not use the
Yes.
word topos, but a different world in which you can talk about statements of, intuitionistic higher order logic. You can talk about whether they hold or not. Here again, we're in this non-classical space where something that you might expect to hold, which is, every real function is either negative or either strictly negative or positive, doesn't hold everywhere. But there is this notion of, oh, actually, where does it hold? So there's sort of refinement of, is something true? Is something false? Of like, where is it true? How much is this true? How can I take that notion of truth and make it more, less of a switch on off and more of a something interesting that you can look at by itself. And you're saying this then informs a further refinement of logic where you have explicit ways of talking about these new tools that you have to talk about the measure of truth and push those back into the logic and give those tools back to synthetic mathematicians that can now, talk about the logic of these things. And it sounds like you were about, and sorry, I interrupted you, talk about this specific tool to talk about local reasoning in these kinds of topological objects. Were you? Is it a modality?
Well,
Sorry, I'm
okay,
trying to
so this is
guess.
a good question. So I know the recent work by Ingo Blechschmidt and his co-workers on algebraic geometry, synthetic algebraic geometry makes a move like that. They have an axiom which gives you this kind of idea that you can do things by pieces. So I'm not actually familiar. This would be an interesting exercise to say, oh, okay, so you're in a sheaf topos. Can you formulate an interesting synthetic axiom or that will allow you to say, oh, I can do the gluing construction.
Right.
I can use it locally and then put everything together. That would be actually a nice exercise. There should be a way to do that.
Yes, I'm
Right?
not the right person for that exercise, but I
Yes.
agree. It would be a good exercise.
Right. So maybe one thing here to keep in mind is the following. You can use your brain to carry out a logical argument. And this is something we're trained with. And it seems like evolution has given us some ability to do this. And the moral of the story is this. You can carry out such logical arguments that you usually call proofs and reasoning. And if you can train yourself to be a little bit careful so that you know how to avoid excluded middle and choice, then suddenly your power to reason logically will greatly improve because your logical arguments will have a geometric explanation. You will think in terms of logic the way you're used to, but the end result that you will prove will be something about geometry of a thing, something about the topology, or maybe computability, right? So that's an important aspect of synthetic mathematics. So
Right.
the point of synthetic mathematics is you are just doing the usual thing of proving things, and maybe you're talking about countable sets and easy concepts like rings, but the end result is a theorem that is, when you interpret the model, is saying something much more or something completely different. Like the example we had with countable
Right.
sets.
Right. I don't mean to put you too much on the spot, but do you happen to have a similar example for this, say, sheaf of continuous sets over, say, the sphere?
Say a similar example for
this topos of that we just described.
So something like that. Okay, yes, sure. I mean, the first one that I would say is people are told what a sheaf of rings is because they want to do, I don't know, cohomology, whatnot, right? So, they're told what a sheaf of rings is. So a sheaf of rings is a complicated thing. To every open set, we assign a sheaf such that blah, blah, homomorphisms, la, 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 gluing condition. It's a complicated thing, okay? What is a sheaf of rings inside the topos? If you're actually in the topos, it's just a ring.
Right.
So this is also one.
Special.
I'm scavenging Ingo's stocks. Ingo gives these stocks. So you say, okay, so if you are able to prove any theorem about rings intuitionistically, you automatically proved a theorem about sheaves of rings. And I would think that this would be interesting to people who study sheaves of rings.
Because you could just open, I think somewhere here I have a, what is it? Like a classic Serre textbook on algebra, right? You open it, it's full of theorems about rings. All the proofs are like 10 lines or, page max.
Yep.
Bam. Now you magically have those. Now you need to stare at those theorems, right? To make sure that they hold intuitionistically.
Right. So now you, of course, are going to ask how many of those theorems are intuitionistically valid. And the answer is A, more than you think. B, the really interesting one, probably not. The really interesting ones, probably not.
Yeah. And to be honest, let's see. One thing I have noticed as a somewhat amateur mathematician is it is very common in textbooks to see proof of theorem foo, or there exists bar, right? Let's assume that it doesn't exist. And here we construct one, and therefore we get a contradiction, and so the thing exists. So sometimes the theorem immediately uses a non-intuitionistic approach, but it didn't have to, right? Just a tiny bit of extra care could have avoided this situation.
Yes, right. I call that logical hygiene.
Logical hygiene, yes.
Yes, and one has to learn hygiene when one is still young. If you want to brush your teeth regularly, then your parents have to beat it in your mind when at an early enough age that you should wash your hands and brush your teeth. So to my mind, if you want some of these benefits, you have to go through a training phase. Well, okay, either you're trained classically and you think it's a cool idea to when you try to prove P, you just say assume not, because it can't hurt you and you just have an additional
it gives you
right. Yeah. So having this sensibility to how you prove things and knowing whether you use the excluded middle or not, right? That is something that can be a little bit valuable. And we can always draw as analogies with simpler things, okay? So you're going to do non-commutative algebra. Maybe you should not be randomly switching x times y and y times x. You need to be careful. You're multiplying matrices. A times b is not the same thing as b times a, except that this is easier to learn, right? So I don't know. It's easier.
Maybe it's just mathematicians are inured, right? They know that there are non-commutative rings, so sometimes they think, hey, I wonder, right? Is my proof like they think about it,
right?
But yeah, so I like this point, which is mathematicians do this thing all the time, where they go back in their theorems and they say, oh, is this stronger theorem a consequence of my proof? And this is just the same, more of the same, except with something mathematicians aren't necessarily taught, when they're children, which is the foundations of their logical moves.
I think I just realized another good slogan here. Synthetic mathematics is the mathematics you get when you don't consider logic to be special.
Right. That's a great slogan.
Right?
Yeah.
You allow yourself to do to logic the things you actually do to everything else in mathematics. You allow
great.
yourself to
That's great.
generalize, change it, make it strange, you know, because some of the moves mathematicians make can be quite strange and surprising. You allow yourselves to do that with logic. The logic is not a holy cow. See where it gets.
That's a great slogan, I think. And to a certain extent, these to remain unnamed mathematicians who do strange things with classical sets are also perhaps doing this thing, right? Where they're, you know, this famous Whitehead conjecture, you know, that is, you know, false if you assume choice. There are also questioning these sacred cows of foundations.
Right. So in that case, maybe so this is more set theoretic, where you produce models of Zermelo-Fraenkel set theory, which are surprising or show you that certain things are different in certain ways. So I consider that to be essentially the same kind of activity. So it's just allowing yourself to let go of a thing that is supposed to be fixed.
Right.
So the fifth postulate, the axiom of choice, excluded middle, just allow yourself to let go and see where it gets you. And it's just more general, right?
That's very Zen way of looking at the practice of mathematics.
I'm not saying it's easy.
Right.
I'm not saying it's always going to be useful, but it just needs to be useful in a couple of cases.
And also I think it's just worth exploring, right? And I think maybe I shouldn't advertise it like this, but I do think sometimes it's exciting to be able to go back to a textbook, take very elementary theorems, and say, hey, can I apply this synthetic philosophy there and take a simple theorem and prove either a really complicated known thing or a completely unknown thing using this simple theorem somehow. Like, this is tantalizing, right? It feels like you're getting a lot for your money.
Yeah. So in this, by the way, in the topos of countable reals, right? In that topos, Brouwer's fixed point theorem, which says that every continuous map on the closed ball has a fixed point, follows in a couple of lines from Levier's fixed point theorem.
Oh, wow. I've always wondered about that. That's great.
So we have in that topos, Brouwer's fixed point theorem is proved without any analysis, no complex, nothing, no homotopy, nothing, zero, no homology, nothing, right? Because Levier's fixed point theorem the proof is a one-liner.
Okay, but actually, now that I've said this, enlighten me. This proof does not transpose to the classical realm, right? It only happens in this.
No, it works because Hilbert cube, that's the closed interval to the power of natural numbers. That's sometimes called the Hilbert cube. It's the infinite dimensional cube. That one's countable.
Okay, yeah. So that's probably not true classical. All right. Okay, so this delightful thing happens. This beautiful theorem holds in this realm, which seems somewhat strange, but for which you can apply all these, you know, I was going to say classical, all these well-known mathematical constructions from intuitionistic logic. That's fascinating. I don't know. I feel like we've made the point I wanted to hear just extremely well. But so I don't know if we would end it on a high note here. But at any rate, I want to hear any additional thoughts you have on this. And again, I'm putting you a little.
I don't know. So people who are, I mean, if anybody's interested in this, okay, so here's maybe one. Some of the things we're mentioning sound insane, right? Starting from all maps are smooth. Now I was saying things like the Hilbert cube is countable. and they just sound insane and strange and
Yes.
unacceptable. I think mathematics has a sufficient number of cautionary tales about insane, strange things that shouldn't be accepted. Because, going again back to non-Euclidean geometries, but also things like the Weierstrasses, everywhere,
continuous
nowhere differentiable function, the Banach-Tarski paradox. These are all things which are, or the space filling curves were also considered a great oddity. Pathological. So I really would hesitate to call anything in mathematics pathological, even though in some sense mathematics is this. Mathematicians are really good at zeroing in on studying the pathological, but that's another story. So I don't know. No, maybe we can just end on this note that, this is an exciting possibility. If you're interested, there's lots to be done.
I do have a follow-up here.
Yes.
Let's pretend that this hypothetical listener we have is a budding mathematician, or perhaps a computer scientist. Why not? Or just generally an enthusiast, which I guess is essentially what I am. And they want to learn a little bit more about this. What should they do other than like looking you up online and finding your homepage? What should they start reading? What should they keep their ear on the ground for?
So there are specific cases of synthetic mathematics that they could look at. For instance, there are very nice write-ups of synthetic topology. So the names there would be Paul Taylor, Martin Escardo, Davorin Leshnik. He was a student of mine. His thesis is very thorough. Then there's this new work of Ingo Blechschmidt on synthetic algebraic geometry and his co-workers, which might be nice for somebody who is knowledgeable in algebraic geometry or algebra. Then there is work by Yannick Forster and Dominic Kirst and their group on synthetic computability. And again, Yannick Forster's PhD thesis, I think, is a very nice write-up that explains ideas of synthetic computability.
Yeah, we had Dominic on this podcast. He explained we had Dominic explain the incompleteness theorem on this podcast. Which is
there you go. Then there is the work on synthetic differential geometry. That is Anders Koch, had some nice texts. John Bell has very nice texts. I think it's called The Primer in Infinitesimal Analysis. So that one I would recommend highly, because it is careful in explaining what's going on and is also quite intuitive. John Bell.
Great.
So that's another one. Synthetic domain theory is maybe not so easily accessible. There's lots of it from the 80s and the 90s, but it's maybe technically a bit more unapproachable. So of all of the ones that I mentioned, I would definitely say first go with John Bell's text, An Invitation to Smooth Infinitesimal Analysis, and a primer of, one of them is a booklet and the other one is just a PDF on the internet. So
great.
I don't know if you can post links somewhere close to your podcast.
I will, if I have the patience to gather them. Okay. And I'll make
if people Google some of the names that I threw out, they should be able to find it.
It'll be a process, but I'll get the word out. Let's see. You did mention a textbook that I've often wanted to buy and just never had either the patience or the shelf room, which was Bishop. Is that worth reading, or is it?
Bishop's? Okay, so there is a later edition which is Bishop and Bridges, Douglas Bridges, Errett Bishop and Douglas Bridges, on constructive. So what is it called? Foundations. I'm reading it off my shelf. Foundations of Constructive Analysis. Well, okay. So first of all, in a way, you should have it because it's a Bible. It's like a Bible a little bit. So that's one reason to have it. It's a very nice piece of text. I mean, you read it, you say, okay, this just reads like normal math, but hey, they really didn't use excluded middle.
So if you're, a bright undergraduate student or a bright graduate student, you open this book, you're not going to be like blindsided.
No, I think that was actually one of its strongest points, was that it wasn't strange or unintelligible or full of some strange concepts that only Bauer understood. It's just ordinary math. I mean, he literally goes, he says real numbers, Cauchy sequences, Taylor expansion, everything. You have to be careful to see where the differences are.
Great. So you could open that book, take any theorem there and say, hey, I know this theorem is going to hold in any of these toposes that admits an interpretation of intuitionism.
Yes, with the proviso that they're using countable choice.
Oh, yeah, okay.
Yeah.
Okay, cool. Also, let's see, the effective topos. This is a reminder to myself, but I'm not sure there's anything better than, let's see, Phoa, maybe?
Phoa's notes are good. I mean, Martin Hyland's paper on effective topos is very good, but Martin Hyland's writing requires one to know a lot.
Yeah, the language.
Usually, yeah.
Okay.
So realizability, I mean, there are general texts on realizability, like Jaap van Osten's book that has plenty.
Great. Yeah, I've
if you want to see concretely how, say, synthetic computability works, you can look up, what would I say? Maybe my paper on fixed point theorems in synthetic computability.
Yeah, to avoid you the embarrassment of having to plug your own paper, I can say that paper is fantastic. I've looked at it.
I mean, because it literally does synthetic mathematics, right? You get to see how it's done. That's the point. That's why I'm mentioning the paper.
Yeah.
It's not so involved with building models and meta-theoretic analysis of what's going on. It just goes like, let's just do it.
Yeah. I think that's great.
That's why John Bell's primer on primer of smooth infinitesimal analysis, or whatever it's called. That's why that one I recommend so highly. You know how he calculates the area of the circle? By subdividing it into infinitely thin isosceles triangles.
Oh my gosh.
And so it's a valid argument,
Greeks, right?
But we know it's valid.
Yeah. So this is like, how to say, not trying to make a pun here too much, but the Platonic ideal of like the naive reasoning steps, the Greeks made and Leibniz made like you can make these naive arguments and also know that somehow they're perfectly valid.
Yep.
What I think Tao calls this the third phase, right? The first phase is you have naive ideas of how things should work. The second phase is you actually learn how to do precise mathematics, reason with equations and axioms. And the third phase is you have intuitions, but you know how to move between the intuitions and the precise mathematics. But this is kind of elevating that, where you can use
Right. So we are, in a sense, what we're elevating here is the intuitions of people who discovered this in this, what was it, 16th century? We know how to make those intuitions precise nowadays. But they didn't, and Cauchy didn't, and Weierstrass didn't. And so they replaced those ideas with something that they knew how to make precise.
Right. Yes. And this, I mean, I talk about this a lot, of course, the revolution of like formal mathematics and figuring out how to actually express these things precisely. But now, we're coming back to this original intuition and showing how that can be put in more solid ground. All right, this is great. These are actually excellent concluding remarks if you want to stop here.
Sure, fine by me.
Great. I will try and post a bunch of links, to your page so that people, if I mispronounce things or if they don't know how to spell it, they can try and find it. But this should be exciting.
Okay, and, if there are links that you are looking for and you don't find them, send me an email. I'll send you the links. Like this John business.
Great. I will also mention in passing that Andrej has a very fascinating and excellent blog.
Which I should write to more often.
Well, that's true about every blog ever. I'd say even the stuff that is there, I agree you should write there more often, but even the stuff that is there is fascinating and it's well worth reading. And
so here
yeah.
you can save this one. Oh, I'm chatting as a guest. Okay, whatever. Well, the link went through.
Yeah, no worries. I will add the link to the description. Great. Yeah, and Andrej can be easily found online. He has great videos. We briefly mentioned the stages of grief of constructive mathematics, which I think is a fantastic talk to watch if you're interested in more of this kind of dialogue, so to speak. And yeah, I hope you had fun. I hope.
Yeah, thank you so much for having me. This was great fun.
Great, thank you so much.
Okay. Yes, and thanks
there,
for actually running the whole thing. It takes some effort.
Oh yeah, thank you.
Yeah.
All right.
Okay.